Well, I figured I'd better do a follow-up video from last night's video regarding the micro SDX from my new little station running the electric dipole. I'll start a beacon macro. Okay, so she's now transmitting, this time on the 40 meter band. I'm not sure how well that'll show. So, and that's the power there. So that's on the 20 volt scale. So about 5 watts, probably peaking just a Mickey here. I shouldn't say that. Over 5 watts. So I'll just show how this is set up and where the antenna is, etc. So first of all, what I'll show is that now this is a very sensitive meter, looking for anything in between me and the element in the E field direction, and you can see that I've got no RF in the shack. Okay, now where the coax comes off the ground through the window, we can also see there's no RF on the coax shield, and I'll now track outside. So this is where the coax comes out of the window, and you can see that it's not exciting the meter. I think most stations, if I went to most people's stations on their nicely set up antennas, this meter would be going off its head. Now of course, once the coax is on the ground, even if it was active, we wouldn't really see it on the ground because it would couple. Now it's going across there and running over and up this way, so I'll go down there now. So now I'm down at the other side, and the coax is coming down here, taking a little bit of a U-turn, tracking along the ground. So it's a very lengthy run of RG213. And then, you know, it's taking a bit of a wander here. And then here is where it goes up. It's quite high. Now, let's see if I can get this into shot. There's a point, see that little module? There's a module where the coax then connects to the new transmission line, which then I'll actually swing around and get another perspective here. Bear with me. It's a little bit tricky because this one's quite high up. But by the way, it doesn't give it all that much of an advantage being high up. It's one thing I've noticed about these antennas. So you can probably see the little module there. So that's where the conventional transmission line ends. And this module makes sure then that anything from here onwards is in LMD mode, which is longitudinal magnetodielectricity. It converts to two versions of the electric field signal that are inverse. And the transmission line has a floating shield and 3 inner conductors. 2 of the inner conductors are driven by this section. Now, the third inner conductor is basically allowing for any back EMF from the electric dipole to come down and then come back up again, and also capacitively couples with the 2 opposing in E-field conductors inside the shield. And of course the shield, although it's connecting to nothing, is the sum of all of the activity inside it, which equals 0. Now it can of course act as a path for currents to run along, but essentially the dipole itself, it has the hottest potentials between the 2 short elements. So I'm going to have to bring that down to show you. First of all though, standing sort of at the base of this system and holding my meter up, you can see that it's also not being very excited. So it's not that the coax is doing the radiating. Most of the effective radiation is actually coming from the differential between the 2 dipole elements way up there, and radiating an equivalent to a TEM wave from 2 very strong alternating opposing E fields. So now I've just brought the whole thing down so I can show a little bit closer. So its own transmission line, its unique line is here, okay? As you can see, that's just bunched up on the ground here now because I've had to bring it down. And this is the module where I connect my coax to, and this is where the conversion takes place and where it then feeds to the new transmission line. This floating wire here is from the shield. If I wanted to actually give it a radial leg to direct the propagation, which I can do. Now, so as you can see, it does have a braid, and then there's the 3 conductors up the middle. 2 are being fired at the same time, so the impulses travel together, but one is a negative while the other is a positive, and vice versa. But what's interesting and very important to note, though, that these are not currents, and the reason they're not currents, there's more than one reason. The sum of the negative and positive fields traveling forward in the same direction create cancelling magnetic fields, which cancels the notion of currents. Furthermore, this whole system ends up running with 100% reflection at the same time. So the reflected signals which would be coming back, are also at the same magnitude as the forward signals. So again, no currents. It just becomes alternation in the E field simultaneously throughout the whole thing, like changing plates of a capacitor. And the transmission line then comes up the middle of the bottom short dipole element, which also has a torus on it. I'll explain why in a sec. Then we actually have the separation, and then there's the top dipole element. Now these are very, very short, so basically this element here, the top of this bottom element, is about as long as from my shoulder to my fist if I stretch my arm out, so very, very short. Now, so essentially it's a dipole, and without the torus on it, it'll work great. But now it's an electric field dipole. So if we freeze time, and let's say this one has a very strong relative positive with respect to this one, relative negative, and the whole notion is not, as we're accustomed to, about coherent currents running up and down. 40 and 80 meter wavelength, well, that certainly wouldn't make sense on something this size. But if you imagine these changing their electric field magnitudes at frequency, then it's like a capacitor opened out. If this was a capacitive plate this way, and this was a capacitive plate this way, the electric field lines would be between them. But we take that plate and we straighten it up this way, and we take the bottom plate and straighten it out that way. The electric field lines are then curving around from each side from one to the other, okay? Now, we already know, with our basic physics understanding of how antennas work, that if the E vector has this curve, that the B vector would be going around it, basically as changing charges are moving, for example, creates the rotating magnetic fields. But if they're moving from here down and here down, they all create the same rotation, which means one very large rotation. If these are really high magnitude, those electric field lines traveling down, for example, trying to connect back to the other side, are huge and all creating a very large rotating magnetic field. So this is how I get my transverse electromagnetic wave. Not by the direction of currents running up and down a wire and using the H fields that result from that, okay? But simply by really intensifying the E field potential between these two, which then causes the TEM wave as a result over the surrounding area in a very extreme degree. Now, the torus here is added for a very particular reason. It doesn't have to be a torus, but so I was explaining the field lines, okay? Now, since the two closest points of the opened out capacitor, so this section and this section, are of course right here, the strongest potentials are right here. So most of the effective radiation is from this point, essentially, arguably. With the way we have to have many different mental models, and none of our physics models are true and correct. Absolutely not. Now, having this torus here on this bottom element means that, and this is very close to the very beginning of it, the electric field line potential from the top element is coming out and across to this. And as we move further up there, it's further out here. So in the most intense point, we've intensified the field line interaction to this angle, which then means we're getting a higher takeoff angle in the TEM wave. So just like we do with a ground plane antenna, except I'm working purely with high intensity E fields. And this is the nature of the system. And now when we look at my HF mobile E field antenna, it's actually using the same working principle. This, though, you might be able to see, it's a bit tough. This is electric dipole. There's two toruses. So I've tried a different approach with this one. I'm trying to get this in shot. But the thing is, this torus on the bottom element is at the very beginning of the bottom element. This torus on the top element is further up the top element. So again, when the intensities start at the beginning, the bottom element gets the maximum intensity first and the top one a bit later. So again, it's giving that same curve. So it's just a slightly different way of getting the same approach to raise the TOA. The difference with this one is what is in that module at the start of the transmission line on the other one is all in the antenna here. So all this one needs is a direct connection from the elevated feed here. So this is basically like an extension of coax, and then it has its two sides, the two opposing signs of current, or one swinging active versus a reference, going to an initial regenerative coil feedback loop system that prevents the back EMFs. That then drives up the middle of this, so this is not a direct connection to the output from here. It goes up the middle, and then this system does like my other module and creates the two inverse E field signs, and then it's set up as dipole bottom element, dipole top element. So but to get this type of system to work really effectively, you really need the magic of my amazing regenerative systems, which kind of defy common logic from a typical EE point of view, and even a typical physics point of view. But the proof is in the pudding. That system on the car is actually very close in performance in the far field to this system way up in the air. Being up in the air only gives this a minor advantage. One of the noticeable advantages is the local area coverage. The local area coverage is improved with this being elevated. Far field, there's really not a lot in it between being down low and elevated. Okay, so now, although it's down low on the ground, pretty much, I've just started transmits with the 5 watts, and as you'll see, this is the active, very active part of the antenna system. Okay, so that's the point where all of the RF is coming from. So even when it's up in the air, no, it's not using the entire coax shield for classic currents. The version of currents that is creating the TEM wave signal are displacement currents going on around these elements. And not only that, when it's running at high intensity, those displacement currents are very, very spread. And if you follow the Faraday's laws of induction, of course, when there are moving charges, like charges, traveling in the same direction, they create the same rotating magnetic field, and they can't individually have those rotations. So that magnetic field rotates around a lot of them, and that causes Z pinch. So if you've heard of Z pinch or zeta pinch, that's kind of what's happening. So it actually creates a very large rotating magnetic field, alternating, simply due to the high intensity E field differentials that are alternating between these elements. 7.3, and thanks for watching.